absolutely one of our absolute favorite model systems. You can basically study all of biophysics by studying chemotaxis in bacteria. They have no neurons. What they do have are nonlinear operations, and that's the big theme here today. Whether you're doing it with a biochemical network or you're doing it with a neuron, if you can just make some input stimulus and wire it linearly to an output behavior, why not just wire up your sensors to your actors? There's nothing to compute, essentially. All of the computation is about these nonlinear transforms. In the brain, it happens to be fairly nuanced and complicated, but it might just be, multiple E. coli swimming around in there, effectively. All right, so the reason a condensed matter theorist is interested in this, because one neuron typically doesn't make a brain. You can do a computation with one neuron, but a brain is a collection of many neurons, and we'd like to understand how many neurons are different from one neuron. So now I'm going to show you what some neurons are. I'm going to give you a little crash course in the dynamics of neural spiking, which is the sort of currency of neural communication in the brain. I'm going to go through this quickly because it's kind of a fun background until we get to intro to information theory. If I start going too fast, I designate all of you as my brakes. And if I'm going too slow and it's stuff then we'll have a vote. All right? If it's going too slow, then we'll say how many people think it's going too slow. If it's more than half, then yeah, we can accelerate. I've prepared a lot to show you. Okay, so this is a picture of a neuron. Neurons are just specialized cells with all these funky processes. They have input dendrites. They have a soma that you're used to that does all the normal stuff many of you are familiar with, and they have an output channel called the axon that can be ensheathed in myelin, which helps propagation of that electrical signal down the axon. Your brain communicates with these electrical signals that are sent down these axons. These are changes in the voltage across the cell membrane that happens very rapidly and very reliably, and makes this neuron a bistable or excitable system. So what happens when a spike is traveling, say, down the axon is that you'll get sodium rushing in, potassium then rushing out, and then a pump that resets the sodium and potassium levels. So we can go into that a little bit here. So here is what you might see if you have just a neuron at rest. It might be at a minus 60 millivolts potential relative to the sort of extracellular solution that it's sitting in the brain. And if I give it a single stimulus and it's above threshold, I'll get this really funky, completely different behavior. So I can give a sub-threshold signal and I'll just see a relaxation back to baseline, slightly larger signal, relaxation back to baseline, but bam, when I hit this threshold, I get this spike. This spike travels down the axon, jumps across the little gap between the neurons, the synapse, and there's with some release of neurotransmitter that starts the whole process again in the downstream neuron. Then there's another electrical potential that travels down that axon. So neurons are interesting bistable systems. They have this resting state, they have a spiking state, and they can have a sustained sort of recurrent activation state. So we're going to dig into this a little bit because studying the complex kind of dynamics of these neurons is going to be reminiscent of a lot of the things many of you do in cellular systems where you study the dynamics of various chemical signals inside cells that aren't neurons. So here in this initial rising phase or depolarization phase, so the neuron is polarized relative to its surrounding solution when it sits here at minus 60 millivolts. You can have a cation rushing in, typically sodium rushing in, or an anion rushing out. There's some symmetry here. Cation out or anion in, and then cation in or anion out to restore you to your baseline potential. How do you set all of this up? How do you set up this minus 60 millivolts potential in the first place? Well, your neurons are cells, and cells are lipid bilayers with all this stuff that goes through them, right? And all that stuff makes that lipid bilayer a semi-permeable membrane. So let's just take a little chalkboard interlude to look at that a little bit more. I told you I was goofy. I wasn't kidding. All right. So over here, let's remember high school electronics. So if I have a capacitor, and I am charging it up so that there's a plus side of a capacitor and a minus side of a capacitor. And how do I do that? Well, I might just hook it up to a battery. That creates some charge on the capacitor. And the current that flows across the capacitor, does anybody have this at their fingertips?
Does everybody remember what a capacitor is?
Does everybody remember what a capacitor? All right, we're just all waking up together. We're gonna like evict your jet lag by the end of this with just raw enthusiasm. Okay, so the current that flows across the capacitor is related to the capacitance times dV dt. Okay, and this is the fundamental equation that we use for figuring out the dynamics across this lipid bilayer in a neuron. So here we see the capacitance is the membrane capacitance of the neuron, and it's related to the sort of geometry and physical properties of this thing. How big is your cell? How far apart? What's the dielectric, effective dielectric that's inside? These are all the hydrophilic heads and all the hydrophobic tails that stick together in your regular lipid bilayer. Yeah? Right, you're always measuring a voltage change across this membrane. So the voltage inside the cell will be different from the voltage outside the cell. So if you think of the outside as the bath as 0, the inside is minus 60 millivolts. Everything, so that's a funny thing, right? Everything is, there's this whole large inside the cell. So the axon is, the outside of the axon is outside the cell, and the inside of the axon is inside the cell. The axon's a little tube, and so there's still an inside of it, if that makes sense. It's, in particular cases, it's big enough that you could even put an electrode in there into the axon and measure the inside and outside. So we're going to talk about, in just a second, I want to tell you about the first Nobel Prize in theoretical neuroscience, which was actually a Nobel Prize in physiology and medicine to Hodgkin and Huxley back in the day. And that's exactly what they did, is they found the inside of that axon, because the squid has a really giant one.
Did you probe who knows this stuff?
Yeah, how many people know something about neurons? I'm calculating that's about a third. So I think it's okay that we're going over this. But if those of you who know about neurons, you can take a nap, but you'll miss the jokes, so stay with me, and then you can answer the question.
Who's a neuro expert? Who actually works on neuroscience? Okay, so that's like
Carolyn, Shawen, I'm trying to remember everybody. I have name salad in my head right now.
Okay, but it's like 4 people.
Okay,
So we're fine.
So we're fine. All right. Okay, so the membrane potential is this. There's a dV dt, and we're going to want to measure the voltage across a neuron, and it's usually written as minus I. That's a convention. Inward currents are negative. So let me tell you a little bit about cells that spike in mammals and in squids. So there are these mammalian myocytes. Those are the muscle cells that are in your heart. So the ventricular myocytes have a funky kind of cell shape. They're kind of like boxes. We're going to draw them as a box, a little parallelepiped, which is spelled like this. Right, okay, so it's 10 microns thick, it's like 30 microns wide, and it's roughly 120 microns long, and these are the things that are in your heart muscle, and muscles spike as well. Now here, this top surface and this side surface, all of the sides of this box are lipid bilayer capacitors, okay? And I'm going to tell you that outside, so out here, in a cardiomyocyte, in a mammal, there is 5 millimolar potassium, there is 140 millimolar sodium, and there is about 2 millimolar calcium. those are just some of the ionic species that are really important to neurons and important in all kinds of cell signaling. Now inside here, inside this box, inside, we've got 140 millimolar potassium. We've got 10 millimolar sodium, and we have basically almost no calcium. Okay? So your neurons are essentially bags of potassium. They're bags of potassium. How do they become bags of potassium? These channels only let pass certain ionic species. They're not just holes. Let me see if I can hook this on a little better. Still good? Okay. They're not just holes, gaping holes. So what you have in neurons is you have bags of potassium sitting in a sea of other ionic species. Okay. Now this is the mammalian myocyte. There's also a squid giant axon. It's called a giant axon because it's big, not to be confused with a giant squid. The giant axon of a giant squid is probably something to behold, but already the squid giant axon is something pretty remarkable. We're going to talk about the dimensions of it in just a second, but let's talk about what's inside and outside. So an axon is like a tube. There's an inside and outside of a tube. Outside there is 20 millimolar K plus and 491 millimolar sodium. I'm going to forget about calcium for a second here. Inside there's 400 millimolar potassium and 50 millimolar sodium. Okay, so you'll notice a few things here. Again, the squid giant axon is also like our mammalian cells. It's a bag of potassium, a little bit of sodium in it, but it's basically concentrated potassium relative to the outside. You'll notice that there's a heck of a lot more salt outside the squid. Anybody have an idea why? Sea salt. They're ocean-going creatures. That doesn't mean that they're full of sea salt. You know, they're not. They make their own internal fluid, but it's definitely saltier than you might expect for a land-based animal. But the difference, what matters here is the ratio between these two. Because what are we doing when we set up that semi-permeable membrane? We're making a concentration cell. So again, let's just do lightning fast. Now maybe we're stretching into, I don't know, a tiny bit of physical chemistry, tiny bit of maybe, I don't know, maybe you learned this in electronics or something. So a concentration cell. Okay. So imagine that this is our lipid bilayer. And this is inside the cell, and this is outside. So what I said is that there's a lot of potassium here. And then there's just a little bit relatively outside. So what's going to happen? If we have a semi-permeable membrane that allows the passage of potassium, which way is the potassium going to flow? There we go, to the outside. Now what's going to happen if we have potassium chloride here? Say we have potassium chloride, but only the potassium can go. So it's a semi-permeable membrane. So only a potassium can go. If only potassium can go, it will flow that way, but then eventually we're going to be building up a charge. Right? We're going to build up a charge. So we've got a diffusion gradient where the potassium wants to diffuse across the membrane, but then we have an electrical gradient. We have an E field. And that's going to oppose further flow of the potassium. So what do you want to think about? We want to find the equilibrium point, right? We want to find the point where these forces balance each other out. All right. So let's just, I don't know, let's do a little electrochemistry, which is always, I don't know. maybe some of you were chemists. I did chemistry and physics as an undergrad, so I have some affection for this, but I know it can be a little bit unappealing. So here's our chemical potential. What's our chemical potential? Well, we've got some constant. That depends on the stuff that we're in. That's going to be the same inside and outside, so we're going to forget about it. Then we've got something that depends on the diffusion, on the concentration. So we've got gas constant, we've got temperature, we've got natural log of the concentration of our ionic species. Then we've got something related to the voltage. Z, this is like the charge. So it'd be +1 if we're talking about potassium. If we're talking about calcium, it'd be +2. Talking about something like chloride, it'd be -1. We've got Faraday's constant. This is where chemistry gets kind of ugly. There's all this stuff in it. That's okay. And here we've got a voltage now across the membrane. So just like in a regular potential, we want to move from higher to lower chemical potential. So at equilibrium, we're going to say the chemical potential inside is equal to the chemical potential outside. Okay? So let's rewrite this. And we've got different concentrations of our ionic species inside and outside. And we're going to have a voltage drop inside and outside. So let's write this as voltage inside minus the voltage outside. We do that because we often set the voltage outside to 0. We ground that. We only care about the relative voltage. All right? So what is, if we write down these equations, what is V inside minus V outside when we rearrange terms? Shall we do it together? How about if you take 1 minute? Just limber yourself up. Little basic algebra here. Hardly. So write mu inside is equal to mu outside. And this is just a mu naught. So I'm going to make that a 0. If you'd like to call it. What? This, oh sorry, this is just this. Good? Yes, very good. So out over C in. And what's in front? Good. Good. Everybody happy? Very good. So what this tells you is that at equilibrium, the voltage difference between the inside and the outside of a cell is going to be related to the ratio, the log ratio of the concentrations. So even though the squid is saltier, it can have the same sort of rough dynamics if its concentration ratio is about the same. And this is on a log scale. This equilibrium potential is called the Nernst potential. And there are various Nernst potentials for ionic species inside neurons. Okay? So just to give you a few of these, the Nernst potential for sodium in a squid giant axon, you could work it out, but I'll just tell you what it is. It's plus 55 millivolts. And the Nernst potential for potassium in the squid giant axon is minus 72 millivolts. So you can see that if the voltage drop across the cell is about minus 72, you're not going to be pushing potassium around at all, but you're going to have a really big driving force on your sodium. Now, a lot of the times you're going to have that sodium channel clamped down, and in a voltage-dependent fashion, you're going to let it open up. And what's going to happen when you open it up? Is the sodium going to go in or out? If I'm sitting at minus 72 and I open a sodium channel, it's going to go in. Very good. This is all, I mean, you know, we're physicists, so we're okay with a flipping of a sign now and then, but this is one where it matters. So we're going to have sodium rushing in. And in a voltage-dependent fashion, then those sodium channels are going to close, potassium channels are going to open, we're going to have potassium rushing out, and we're going to get these excitable dynamics that were first really, the first really quantitative description of them was given by these two chaps. This is Hodgkin and this is Huxley. They worked together. They got the Nobel Prize in 1963 for work they did the 40s and 50s. They worked together in Plymouth, England, and they worked on the squid giant axon. So here's the scale bar for this guy. So a mammalian axon is here, this circle is 2 microns in diameter. On the same scale, here is the squid giant axon, 800 microns in diameter. That's the better part of a millimeter. It's so big, you can thread a wire into it. And that's exactly what they did. So the giant axon is this bundle, bundle of lipids. So there's an inside and an outside. And this ganglion controls important sort of expelling water reflexes in the squid.
Where is it actually?
So here is the stellate ganglion, and here is the here's the nerve that's going to innervate the sort of, I don't know, when you eat a squid, you eat this part chopped up. That's why it looks like little circles. And here is the giant axon.
So the red thing.
The red thing, lots of them. And it's huge. Okay?
And it's there to get rid of water from.
I think that's right, yeah. So the reason that they were so fond of this is not because they were super fascinated with squid, though they did know something about the behavior of squid. But this was a way to access and catch some of this spiking in neurons in action. So in 1939, they published a letter to Nature where this is one of their graphs, which I think you can tell is a photograph of an oscilloscope screen. And they didn't give really any kind of quantitative description of what was going on, but they were able to measure the voltage in the squid giant axon when it was sending this electrical signal. And this width here is only a few milliseconds. So this is a signal that's hard to measure, and here's the millivolt scale. So this is a spike from a squid giant axon measured in 1939. They left their marine research station on the coast of England on August 30th of 1939 after they sent this letter into Nature, and then they quit working on this, as I'm sure many of you can understand why. Because what happened on September 1st of 1939? Hitler invaded Poland. So that put the brakes on that. Huxley wrote in 2002, we published this result in a letter to Nature in 1939 with no discussion or explanation. In a full paper in 1945, end of the war, we gave 4 possible explanations. All of them were wrong. So they were trying to explain this dynamics, and eventually they figured it out. So oh yeah, go ahead.
What determines the width of that?
The dynamics of the voltage dependence of the opening and closing of those sodium and potassium channels. So you can have, these are called spikes because it's a little blip in the voltage in the cell. It sounds like a pop on an audio monitor if you play this through. But you can have much wider spikes if they're driven by calcium dynamics, for example, in cells, and they can be several tens of milliseconds wide. This is sodium going in, potassium rushing out, and a pump resetting everything.
So like you can mess with the chemistry, and for the same cell you can change.
Messing with the chemistry won't get you there. You have to mess with the channel sort of dynamics, the channel biophysics, and that's a little harder. But yeah, you can muck with this and change it around a bit. You can kind of poison cells in various ways. Let's take a look at how we get there and what channels regulate some of this, and we'll go. Yeah.
So it seems to me that there are 2 time scales, like the electrostatic interaction is way faster than the diffusion, like sometimes. So it seems that there should be like different time scales.
Yeah, there are different time scales for remember these things are small. The distances travels are small, but you're absolutely right. The electric field is going to be set up quickly. This is that whole Nernst potential stuff is for a neuron with all of its channels sort of in a static configuration, and you know, anything that's porous is open, anything that's voltage dependent is closed, and that's what happens. And what we're going to look into now are the very fast dynamics where you open and close basically in this background. You open and close channels and let the ionic species rush in and out before there's any time to reset, like kind of an equilibrium point. Yeah?
Why is there a small bump in front of the spike? I mean, is there an
Oh, that's a great question. Good eye. You're an experimentalist at heart? I'm not sure. I honestly don't know in this why they have that. So you're talking about this little thing. I'll try to find out and tell you next time. But I don't know off the top of my head. This is my theorist yeah. So you can do this in a lot of ways. You can have a spontaneous baseline sort of firing rate in neurons in a dish that you can have, or you can inject a little bit of current, or you can sort of stimulate sensory fibers that then release, that they themselves spike and then release this current. They had the squid giant axon isolated in a dish, and they could deliver current pulses to it to get this. So that might be an artifact of that stimulation. That's my best guess, but since I don't know for sure, I don't want to put it out there. Yep.
So before and after the pulse, are those two different equilibrium states? Or is it
Right.
back to the original?
It comes back to the original. So this is an active reset with pumps. Definitely not equilibrium. This is burning ATP.
But it's on a much longer time scale?
That's correct. That's correct. More questions? I saw one here and one here. Yep.
Yeah, so we study the auditory system, so
Excellent.
I'm kind of used to like this continuous spontaneous behavior. Is that true
Right.
pretty much everywhere? Like is there always a baseline and then if you go below or above the baseline, it's like
Right.
below?
Right. So you're saying that in your cells, you've got a pretty high baseline firing rate.
Right, because it's
Right.
spontaneous itself.
Right, there's some baseline activity of constant spiking. I'm going to show you how you get that kind of dynamics. It depends on where you are in the brain. The background firing rate of neurons in the retina, which is the place that I study the most, are essentially zero. So it all depends on various probably biophysical constraints that sort of got set up over evolutionary time, whether or not you want to spend ATP firing, and maybe you do in the auditory system because you need to be able to respond so quickly and have a temporal code about what's coming in at fast time scale. So maybe there you need to be, you can't just wait and signal sort of some tone decrement. You need to have that constantly sort of online. In the visual system, baseline firings can be very low.
Sorry, it's probably someone asked this.
No.
So if I would to move the offset of this curve, make it at 0, for example,
Yes.
and I would to integrate this curve, would I get 0?
If you moved this to 0, oh, I see. So if I take the area under here so if I set this as the baseline,
Yeah.
and I take the integral of the area under this and this, will I get 0? That's a good question. I think,
So basically what I'm trying to say is that whatever you pump out is
Yeah.
roughly what you get back in.
yeah. That's correct, and it depends on the efficiency of these pumps out here. And you might have to integrate out for some amount of time. But yes, good. Okay,
I have a dumb question.
yeah.
So, I mean, it's 100 millivolt difference between sodium and potassium. Is
100
that-
micromolar?
Yeah. Sorry,
Micromolar.
millivolt.
Oh, sorry, this thing.
Yeah.
yeah,
I mean,
yeah.
Is this just due to differences in concentration?
Yes.
In and out?
Yes.
And so what?
Yeah,
sets that?
because basically the cell sets itself up as a sequesterer of potassium,
Okay.
and it can grab a lot of it and concentrate it, and then it's waiting and it's giving itself a set point where it then can suddenly let sodium rush in, and then it can have potassium channels open that push potassium back out. I mean, the why of it, I don't know.
Yeah.
Why spike with sodium rather than potassium? That's a good question. I mean, cells also spike with calcium.
Yeah.
So you can do it with different ionic species. And we'll see that, you know, this,
But it's like we can think about it as a historical artifact that cells are designed this way that they suck in potassium.
Yes, I think we can take that as our base. I'm not sure if somebody with more you know, sort of evolutionary chemistry kind of knowledge would say, no, sodium's much more, you know, you wouldn't say anything about the abundance of sodium. There's plenty of sodium around, right? Maybe there tends to be more sodium around than potassium, so it's easier to it's easier to set up gradients. But I have no argument for why that would be. We have to know something about probably where this all started in plants or bacteria. Yeah.
So, sorry if it's already been asked, but
Yeah.
where do you replenish your ions from?
You're sitting in this bath, right?
Yeah.
You're sitting in this bath, and that's where you grab stuff, your extracellular space.
That's a different reaction pathway where you.
Yeah, there's a pump that actively resets all of those potentials for you here. And that's another channel that spends ATP to pump. You let sodium in, and then it'll pump it back out. So there's all kinds of ion exchange pathways, and those things are common in all cells. And these have been co-opted in neurons to operate to set up this kind of excitable dynamics. Yep.
These potential are almost in the same range, so they're like -60 to +40.
Yeah, they tend to be around anywhere. There are chloride channels that are have a Nernst potential at -90, but that's really the range, So it's not. It's sort of so. Then we could ask a question of why this order of magnitude. Probably has something to do with the physical nature of the channels that you have and the sort of time scale of what you're trying to get. But I mean, I firmly believe, without any proof, that if biology needed to make a faster spike, it could have. Yeah. Okay, we've got 2 more questions, and then I'm going to force us to carry on. Yeah.
Does it have to do with the temperature, like defining different organisms?
Absolutely, and that's a really big problem actually in a lot of, so one thing that experimentalists like to do with the brain is to chop out a piece of it and put it in a dish and measure it there. And that usually is at a very different temperature than what body temperature would be. The reason is that you've chopped it out and it's dying. If you heat it up, you'll accelerate the death, typically. So that will affect all of these dynamics and especially baseline firing rates. So it's something to keep in mind if you're reading neuroscience papers, and they happen to be sort of in vitro, perhaps how physiologic was the condition that they put things in. And there was a big, sort of reckoning in the slice physiology field some years ago when they were studying plasticity, and they found that they really needed to be careful about the ionic concentrations they put in the dish and mimicking what you had in the real brain. Okay, one more, yeah.
You already mentioned the pumps pumping the ions back and forth.
Yeah.
What's the ATP consumption of one spike?
Oh, great. What's the ATP consumption of one spike? How much ATP does one spike cost? I don't know. I bet it depends on the cell. Yes, do you know?
No, I
Oh.
don't. But I mean, you can just calculate. Okay, this is my guess. So you just calculate the area under the integral for the positive bit, right? And that will tell you sort of how much voltage that you needed to, like how much integrated voltage you needed to.
The problem with this ATP question is that depending on the channel, we're going to talk about it in just a second, the kind of channels that do this, they undergo conformational changes to then allow the sodium to rush in. And that could cost energy that we're not seeing here. Let's hold that. I don't know. I'm going to leave it at I don't know, and we will try to look that up. So here's the final model that Hodgkin and Huxley put forward. So here is the membrane capacitor, and then they said there are various sort of parallel batteries, which are the Nernst potentials of these various ionic species, and these resistors that have this potentiometer kind of like symbol here with an arrow on it, means the resistance can change. Resistance changes with voltage. And it can also change, it has some dynamics over time. And then this is the one that doesn't change with voltage. This is called the leak. This is kind of a fudge term that says no neuron is perfect, there are some holes. There will be a potential that's set up just by the fact that there's some leak. You tried to make a bag of potassium, it's not perfect, it's biology, there's some leak. So that's what they wrote down, and then they were able to infer the voltage and time dependence of all of these currents. So here's your equation, and as promised, capacitance times dV dt is all of these terms. So V equals IR, so we've got capacitance G is like 1 over resistance, and then here are the voltage differences between the current voltage in the cell and the Nernst potential of that ionic species. There's a leak potential, there's a sodium potential, there's a potassium potential. And then you have these prefactors. So there's a term here that's sort of like the conductance of the sodium, and then you've got some time-dependent factors. These have their own differential equations. So this little m here, there's a dm dt, h, there's a dh dt, n, there's a dn dt. And these look rather complicated. It gets a little bit worse even because these terms inside the differential equations for these prefactors can also have some voltage dependence to them. Okay? So here you see alpha has some exponential dependence on the voltage, beta as well, and so on and so forth. And they all have so when they published and they got the Nobel Prize for the technique that they used to figure all this out, they had to fit all of these little parameters. And they didn't have like big computational machines to do this. There was a lot of trial and error. Yeah?
So what are the variables M, H, and N?
Right. We're going to talk about that in just a second. We're going to dig into that. See here, this potassium conductance has an n to the fourth. We're going to talk about why did they put n to the fourth, what their guess was, and how good a guess it was. And then the sodium's a little bit more complicated, and I'm going to leave that for your further reading. Yeah. Yeah. There's a lot. Yeah, so this would be one of those, like, what's our VC dimension on this? Like, how much data do we need, and to squeeze down how well we know this? They miraculously got this right within, sort of 10%, which is pretty good. And it changes cell to cell, so these parameters won't be exactly the same. So we're going to talk about fitting the nitty-gritty of a particular action potential versus understanding the overall sort of framework here. All right. Yeah?
So you just got these parameters just by curve fitting?
Yep. Sometimes by eye. Sometimes by eye, which is fine.
Excuse me.
Yeah.
The potential is due to some effects of distribution in the cells, or?
The leak potential?
Yes.
Yes, so there are some non-specific channels that are always open that allow some that are sort of the semi-permeable holes in the membrane, and they have some net composition of letting so much negative in and so much positive out, and that's where you get this like kind of average leak potential. But there are lots of things, lots of holes. The holes are channels, the channels that don't depend on voltage. Yeah, absolutely. Okay, crash course in neuroscience carrying on. All right, so what they actually won the Nobel Prize for was the voltage clamp technique. So what they did is, here's a, sort of artist's rendering of a squid giant axon in a dish in a bath of saline solution. And all they did was hook up, well, all they did, this was a great innovation, because if I want to measure this ionic current, I can measure that, but I don't know where it came from. I don't know if my conductance changed, that G term, or my voltage changed. So it's hard to separate these things out. And this was their way of separating things out. So here is the piece of the squid giant axon. Here are the two wires that they were able to thread into the squid giant axon. Why? Because it's huge. And this is an example of using a really good use of a model system. So they've got a little amplifier here. They're going to measure voltage. They're going to measure current. And here, they're going to send a command voltage here. So they're going to set the voltage. And that means that whenever the voltage across the squid giant axon changes, they're going to compensate for it with some current until you return to the command voltage that they set. So they're going to clamp the voltage across the squid giant axon. And by doing that and monitoring what the measured current that they have to deliver to do that is, they're going to be able to infer what current was flowing across the squid giant axon here. So they just have to be able to do that quickly. And I think I'm going to try to draw this out for you. This is a simple, we can think about this as a simple 1D dynamical system. So let me redraw this. So, okay, or let me just talk about it here. So if the voltage across, so we're grounding this bath, so outside is set to 0. That's our reference electrode. We're going to say that's 0 millivolts. So if the voltage inside the squid giant axon is smaller than the command voltage, so here we're measuring in that minus sign input there, if it's smaller than the command voltage, then we're going to send a current that depolarizes the squid giant axon to return it to the command voltage. Similarly, if the command voltage is smaller than the voltage in the squid giant axon, if the squid giant axon voltage is above the command voltage, we're going to send a current that hyperpolarizes the giant axon. So it's like a 1D dynamical system. So if we have V and dV dt, dV dt is the current we're sending. Here is our operating point. Here's our command voltage. And in the voltage clamp system that they set up, they could move this command voltage around. So here dV dt is positive, here dV dt is negative. So if the voltage is down here, if it's less than the command voltage, we're going to have a dV dt that's positive, and then we're going to return the voltage to the command voltage. If the voltage here is here above to the right of the command voltage, we're going to have a negative dV dt. So dV dt is going to go negative. We're going to send a current that hyperpolarizes the cell. So this is just this 1D system, and this is V command as the stable fixed point. That's just another way of drawing your little op amp there. Okay. All right, so what they were able to do was to make steps in this command voltage from, say, 0 millivolts or negative, here we start at negative 60 millivolts, step up to minus 30, step back down. And then they could measure the current that's flowing into the giant axon. And that's going to be a combination of things that they inferred were sodium and potassium by doing some clever chemistry. Then you could step it and take various steps here. Here we go from minus 60 up to, say, plus 45 and then back down. You get this cyan curve, and so on and so forth. So by doing some chemistry and algebra to separate the sodium from the potassium currents, they could eventually get these guys, the conductances. So the current is your conductance times your voltage, V equals IR, and G is like 1 over R. So they could infer that the sodium conductance looked like this for different steps in the external voltage, and potassium looked like that. So we're going to take a look at potassium and try to understand how they understood this. This is some eyeballing. So first of all, let's erase this. We don't really need it. Okay. So what this looks like, if it were just a capacitor, right, and we step to the voltage, it would look like this. Well, my drawing skills leave a little to be desired today. It would look like this, exponential rise and exponential fall, right? You guys remember charging up a capacitor, discharging it. It looks like that on the right side. It doesn't look like that on the left. There's a bit of a lag, and it gets a little bit sharper as we increase, but as we decrease, it gets even laggier. Okay, and these shouldn't be crossing like that. Let's keep it all kosher. Okay, so they had a look at these potassium conductances, and they said, this kind of looks like something that goes like 1 minus e to the minus t over tau. This is time, in case that wasn't clear. And with a little bit of trial and error, they say it looks like it's raised to the 4th power. I kid you not. And here, this just looks like an exponential decay. Okay, so this is regular. Okay, and this is this thing. So what did they hypothesize? They hypothesized that there were some species, so they called these particles, and they said that they could be in an active versus a passive state. And they said that there had to be 4 of them. 4 of them had to be active for that potassium channel to open. But then only 1 has to go back for you to close. So they said that this looked like something raised to the 4th. You needed 4 things to happen together. They're independent, they all have to become active, and then as soon as one of them closes, you shut down. And that's why your time behavior looks funky. It looks like, you know, you've got 4 things need to happen to get going. Only 1 thing needs to shut off to get you that exponential decay. So what they wrote down, they said n was the fraction of particles. They had no idea what these things were. Particles in an active, or let's call it permissive state. Active or permissive meaning you can allow potassium to flow through. And they just said that there was some dynamics. And those alphas and betas are exactly what's in the dynamics that they wrote down for the potassium term in the voltage. So they had no idea. There was no what the channels looked like. They didn't even know there were channels. I mean, these are just guesses. They just put this power of the 4 in, yeah.
Sorry, is this should be like n minus 1 going to?
No. This is the fraction that are permissive, so this is becoming permissive, and 1 minus n is the fraction that are not. So they're becoming permissive or not. So if we then, you know, fast forward to the 80s and 90s, where you can do X-ray crystallography of potassium channels, you find out that they look like this. Do you notice anything about this potassium channel? A spiral. That's sort of nice, but anything symmetry to it? It's chiral, yes, but there are 4 pieces. there are. What part is the channel? The channel is here. So you might be more familiar with these kind of diagrams. So down the pore, you've got a bunch of helices and then some pieces, and these things undergo conformational changes, and all 4 of them have to open for you. All subunits have to open. So that's why I call this the first Nobel Prize in theoretical neuroscience. So where did they get all these equations from? They're Kirchhoff's laws, they're 4 ODEs, and they guessed, very educated guesses, some voltage-dependent rate constants. So here's n again, and here's alpha and beta. So they guessed some of the dynamics, on and off, which is kind of amazing. And this works really well. So in their later paper, here is an observed spike and a model spike governed by these equations with those parameters. Can you tell which one is which? Let's have a guess. So here's B and D. Or there's just top and bottom. So there's A, B, and C and D. Who thinks A and B are the real neurons? Why not? Are you seeing something? C and D? Who thinks these are the real neurons? Oh, we just don't have a lot of voting going on. Okay, well the voting was correct, but I can't really squint at this. These are the real, this is the real cell, and this is the simulation. So it's pretty impressive. They did a good job. This is fitting. Yes, this is fitting. They just happened to guess right. They didn't know about the channel. They said from the dynamics, it looks like this is something raised to the 4th power. Lo and behold, the channel was tetrameric, and it all fit together. So it's maybe a lesson in not worrying so much if you can derive everything from first principles. Having a go. Yes, Ilya, and then Nathan? Simon, sorry.
So there's some discrepancy still between the top left and bottom left, right?
So you wouldn't give them the Nobel. Meaningful ones. Okay, what do you think?
Meaningful. I don't know.
Yeah, so which ones are, oh, so the length?
Length is position falls off, right?
This time scale is 2 milliseconds.
The crossover at 0 is slightly at
Yep.
different place.
So some of the things they're missing. There's cooperativity in sodium channel opening that changes a little bit the dynamics of the opening. There are other channels at work here to reset. So there's more than just a kind of pump reset. This return to baseline has a different dynamics, and that's very complicated. And there are other voltage-dependent things that were only discovered in the 90s that govern this reset. And sometimes the squid has them and sometimes they don't. Charlie Wilson has made his whole career sort of digging into the details of all of the different, like the 20 different channels you need to consider to get the spike just right. But I think this is a pretty exceptionally good first pass. For our purposes, for the rest of my lectures, we're just going to take spikes, as events that happen so fast. We're not going to worry about the dynamics. We're going to take them as little binary impulses that come through. So this is just to give you a little bit of grounding so you know where those little ones and zeros come from. That's the dynamics.
Yeah, I think
Simon.
basically similar.
Yeah.
So basically in the experiment, the fall off is
Yeah.
strikingly linear, and in the simulation there's this little.
Yeah, there's sort of, it's almost like the curvature changes around here or something like that. I think that if you grab a modern model of Hodgkin-Huxley dynamics, it'll have more elements to it than just the sodium and potassium.
Sure, I'm just wondering. I mean,
Right.
Having the experimental data and
Yeah.
this striking linear.
Right.
I don't know. Does that tell us something, or is it just?
Probably. I take a bird's eye view on this stuff. So I'm giving you this as a flavor so you feel like you're getting some education here before we dive into info theory. But you're getting past the boundaries of my detailed knowledge of these things. Yes, so many questions. Yes. Oh, that you want to, okay. Seating the floor. 1, 2, 3, 4.
Okay, so how much better is this prediction in comparison to, like, let's say, between different parts, right? Because if, like,
Yeah.
is smaller than tau,
Yeah.
find everything in series, so eventually just like t to the 4th. And to distinguish one power function from another one, either t to the large and
Yeah.
it's not the case, or it should be like extremely accurate. Right?
This is extremely accurate. It turns out that their guess for the sodium channel needed some tweaking.
Yeah, but let's say like the
Right.
like
So just taking potassium.
5, like in the favor number 5, right?
Uh-huh. Right.
Would it be because
Yeah. That's a good question. And so you're asking what's the tolerance on that parameter?
yeah, like if we take like something random, like we may also get some peak, and if it's some parameters, we get some.
So this part of the spike is from the potassium channel dynamics of the potassium channel's opening. So small changes there could be important. but they are not going to come in that power of 4, I think. But it's a good question. It's a good question. Exactly like, what is the perfect parameter, and is it really integer 4, and everything else is terrible? Probably not.
Yeah, but actually, I have a different question.
Okay, what's your question?
What is the criteria for a model to consider?
Yeah. So I would say, I mean, this depends a little bit on people's taste, but I go back to the sort of philosophy of science here, Occam's razor stuff. The simplest model that fits most of your data is the better model. As physicists, we're trying to always peel things apart and find the most essential components that give you the behavior after. Now, if it turns out that you really care, you think that this sort of linear part is what's important for how you that's the important piece of the nonlinearity for transmitting information, then that's important. I don't know, just looking at it from my scientist eyes, is that the important thing to fit or not? Should we get it perfect? Should we have 8 more parameters so we get this whole shape perfectly, or not? And I want to sort of pound this in by showing you the Fitzhugh-Nagumo model, which tears this all apart and makes it much more simple. So I had 1, 2, 3, 4. Yeah. Many. Yeah. That's right. This is one experiment averaged over many potassium channels opening and closing. There are differences in the density of the channels is not homogeneous across the whole neuron. The neuron can have particular kind of inputs and output stations that makes the neuron more than just one nonlinear processor. It can actually be like many neurons in one. So that's important. But here, there's lots of them, and they're kind of evenly distributed along. Yeah.
So my question was, you hinted at this, but so for the potassium, there was a tetramer, and that explains the
Yeah.
What about for the sodium? What is the structure?
For the sodium channels are a little bit more complicated, and they have a kind of ball and chain activation and deactivation part. And part of that is maybe in the M3H dynamics, but not completely. And sodium's just a bit more complicated. But it was a good first pass.
Okay. And also, so for the potassium, to open it makes sense that you need the cooperativity.
Yeah.
So what are the dynamics for closing, and why can you do it so quickly?
You can do it quickly because essentially, if you need all 4 to be open to permit sodium to pass, then if just one of them closes, you stop. And that's that concomitant nonlinearity that gives you the different behavior on the closing. Yeah?
So I am like quite a bit annoyed
Yeah.
at the fact that they just wrote this.
Yeah, sure.
Aren't you impressed? You should be impressed.
I'm not impressed at all, actually. Like, I'm like super annoyed.
So you think that this is bad science and they got lucky, and so it's annoying?
I think this is crap, to be honest. I would not have given them a Nobel Prize for this.
Oh, they didn't get this for this. They got this for this tool for being able to measure and record from neurons. Voltage clamp is one of our most important tools in neuroscience. So just to be fair to them, they got this right with some guessing. But there have been many times when intuition turned out to be correct. And there are, especially I would say in some parts of particle physics, there are some guesses that went into, well, there has to be something else that maybe looks like this. And then you build a theory. I understand. I completely understand.
What do you want them to do? I mean, what do you want them to do? You want them to spend 50 years going after particle number 4, giving it a name?
No, but like, okay, this is not a good argument. Like, literally, they wrote down a function. This is what it looks like, and it looks like there's a power to the raised to the 4. I can write an infinite number of functions that will give me exactly
Which
the
is
behavior.
sort of
So I'm
right.
annoyed. Like,
Right, but that gets it. But it gets. What did Landau do? What would Landau do? I like that. Should be a T-shirt. But no, right. So the question is, I think some of the other questions are on that landscape of all possible functions. How many have these few parameters and fit this well? And is it a narrow valley where this is particularly good, or are there like a dozen things? And actually, I would say Eve Marder and Astrid Prince took this on very directly and said, how many different solutions do cells find where they have different parameters that give you the same behavior? So they did a computational study where they said, how many solutions are there in the stomatogastric ganglion of a crab. So this is, they've got a rhythmic chewing rhythm, so crabs, when they eat stuff, they grind, 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 grind. It's a great system because you can put it in a dish and it grinds, grinds, grinds. And then you can ask, if I need to grind, grind, grind with certain phase, how many different ways can I do that? They did that sort of like brute force computationally, and then they ask, how many different ways does the biology do it? And is there any insight we can gain from that? So I think people both, on both sides of this, but I think I don't know the answer to the question, are there a sea of models with the same small number of parameters that could get you there? I don't know. Yeah?
Let me reiterate the question. So I don't think that it should matter what the exact shape of the slope and all those details, even if it's 4 or pi, so there should be small number of quantities that are actually important, because even have that neuron, right? You can bend it or do something, and then solution will change. Actual physical solution will depend on many parameters that may be different for different systems, and it cannot be the case that it all matters. Right?
No, it cannot be the case that it all matters, and I think that's...
What's important? That there's a peak, that it's narrow, that it's fast, what is it?
So the important thing for, sort of basic neurotransmission is that it's a narrow peak with a big gap, and it's a bistable excitable system. So that I put in a voltage, I put in some voltage, I get no response. More voltage, no response. More voltage, bang, spike. Let's look at that. That's the important behavior. And so I think that even further reduced models capture that and are maybe the thing you want to look at if you're really interested in thinking about this as an excitable system. But yeah, I think then stretching into some of the lovely stuff that Jim Cessna's group thinks about with sloppy models. And I'm going to write down a really nice complete model. I'm going to take a Fisher info matrix. I'm going to take derivatives with respect to all those parameters and ask, how do those derivatives change with the physics I'm trying to reproduce? And are there modes where those exact parameters are really important, and are there other things that are sloppy? And fishing those out makes you define the physics you're trying to capture. And here we have not done that. That's perhaps the basis of the problem. I want to move on. If that's okay, I want to show you the Fitzhugh-Nagumo model real quickly, and then I want to play a game with you and introduce you to information theory and neuroscience, which is the meat of what we're going to talk about. This was my conciliation to Ilya's push that we should have some dynamics in neurons in the beginning. So I did something for you, and now I'm taking something away from you. Okay, so this is Fitzhugh and Nagumo. And what they said is, well, we can make a V a voltage-like variable and W a recovery-like variable. And if I make my dV dt go like something that's like V cubed minus W, and I've got a dW dt that depends on V and W, I can make something that looks like a spike with far, far fewer parameters. Look at how many parameters there are here. We've got like this, who the heck knows where this 0.08 comes from, 0.7, 0.8. These, again, we could get into the details and the weeds about why that's important. One of the reasons that Nagumo made this model is because at the time, it was really hard to simulate complex differential equations. You had to do this with old-style analog computers, but there were tunnel diodes around, and tunnel diodes had that V-cubed behavior. So you could simulate this with an electronic component, and you could make a little box, and you could plug some values into it, and you could play with it. That is one reason why this was, fewer parameters, and you can build it with the technology you had at the time. But even more importantly, you get insight because now we've got a two-dimensional system, and we can plot this dynamical system on a 2D plane where this is the null-cline for V in black, and in red is the null-cline for W. Is everybody familiar with those terms? The null-cline is where my dV is 0 along here. If I move in this part of parameter space, my dV is 0. If I move in this part of parameter space, my dW is 0. So those are the places where those things are stable. And then here, if I go across, say, the V null line, I'm going to switch from 0 to either dV is positive or negative, and here W is positive or negative. So if I start here, okay, this is a fixed point, right? dV and dW are both 0. None of them are changing. The question is it stable or not? Yeah.
I don't know what W and I are.
Yeah, W is just, this is just a new set of equations that are another guess.
So this is not like physiologically, no, like
There's no V3. This is just a voltage-like variable and a recovery-like variable. This is now a removed phenomenological thing that has underneath it Hodgkin-Huxley dynamics, but we've abstracted away. Fitzhugh and Nagumo abstracted this away, and they made this 2D system. And they did this independently at the same time. Okay? So if we happen to be sitting out here, V is increasing and W is increasing because we're to the right of this null line and below this null line. If we're up here, V is decreasing and W is increasing. That's the blue arrow there. And you can see which way we're going from the arrows, the red and the black arrows, as we cross. So it's a very useful simplification, because if I make a voltage excursion here that doesn't take me across this null line, so here's a fixed point. Make a voltage excursion. Here V is negative and W is positive. So I'm going to go up, but I'm very strongly going to go back, and I return to baseline. So I push, I come back to baseline. Now though, if I make a big excursion, this becomes like my threshold. And now my V is positive, my W is positive here. Then I'm going to cross this null line. My V now is negative. dV is negative. dW is now is still positive. Then W is negative, and I come back here. And this excursion time is like the refractory period for the spike. It's like the width of the spike. Okay? So this is now this bistable behavior, and it really shows you how you can get an excitable system out of these dynamics. And it even explains sustained firing, because if I move these null lines around, which you can do by changing ionic concentrations in the cell so that you have something that's tonically firing, now this becomes an unstable fixed point and I get recurrent spiking. I just travel around there all the time. Okay, that is all I'm going to say about the dynamics of spiking. So what are your questions? Yeah. Yeah, absolutely.
So I had this old view of neuron where there is current crossing the axon going to another neuron eventually, like this. But actually the current just crossed the membrane.
Yep, that's right. Right, because when you finally get to the axon terminal, what happens is that there's a chemical signal. And that's going to open a bunch of channels. And then if there's enough of that, you can get a new spike generated downstream. But yeah, thinking of these as having wires between them is true only for sort of exotically flavored neurons that have what are called gap junctions that are really literally like wires between them. But most of them have electrical signaling down their axon. And remember, you've got to get from like your brain to your arm. You might not have lots of synapses, so you might just need to propagate that electrical signal very quickly, and then a synapse takes, some number of milliseconds, and then you jump across. But that electrical signaling is what's important. But you have some wires connecting neurons in the brain too. But for the most part, we think about it as electrical signal travels down an axon, sets off chemical release in that synaptic cleft that travels across the gap between the neurons that's very, very narrow. And that's what restarts the process. Yeah?
Does the stability of the fixed point say anything about the physical system?
Yes, absolutely. Absolutely. Whether or not you're at a stable or an unstable fixed point will tell you something about whether or not your neuron has a baseline firing rate or not. Good. Okay. So here's the ugliest neuron drawing I could find. This is a soma. This is, I don't know what the heck. That's like some sort of aorta, blah, whatever. This is like a dendritic arbor, and here's an axon. if you have a recording electrode outside the cell, you'll just see these little blips. Why they're called spikes is clear. If you're inside the cell, you see the things that Hodgkin-Huxley and Fitsu-Nagumo were trying to model. Outside the cell, there's enough in-rushing sodium and out-rushing potassium that you can pick up those little electric blips, even when you're just close to a cell. And that's how most people record from neurons these days. Either they do this, or they actually image the ion dynamics inside the cell. So when that electrical potential of sodium-potassium releases a chemical species called glutamate at the synapse, what you get in the downstream neuron is an inrush of calcium that then can set this whole sodium-potassium thing off. And you image that calcium a lot of times in modern neuroscience recording. Okay. Neuronal responses are noisy. So here is time on the x-axis. Here are trials. Here's the probability of spike if I average across all these trials. So each little blip here is one of those spikes extracellularly recorded. This happens to be recorded from a part of the birdsong brain that I have worked on called LMAN that is important for song learning and maintenance of song. And neurons are noisy, meaning that from trial to trial, they don't in a whole brain especially, they don't do exactly the same thing. Now we're physicists, so is that noise thermal noise? Is it, what does noise mean? It turns out that the noise in neural signaling mostly comes from that vesicle release, that chemical release at the synapse. So the electrical current comes down, there's, sodium in, potassium out. Next little set of channels, sodium in, potassium out, so that little spike travels down the axon. Then you release glutamate into the synapse. Glutamate's encapsulated in little balls called vesicles, cell membrane balls. That's where the noise comes in. There's variable amounts of stuff in those vesicles and variable amounts of those vesicles. And that's where real noise comes from in neurons. This kind of noise can be partially due to that, so that you do exactly the same inputs to the system and you get a little bit different vesicle release. But this is also this is an alive, awake, behaving bird. And we've tried to get this bird to experience exactly the same thing over and over, but it's not a slab of some magnetic crystal sitting on our bench. It's a biological organism, and there are lots of other inputs that we haven't recorded. So thinking about what you're controlling in a neuroscience experiment becomes really important. Here's a picture of how people make these recordings. This is an electrode array, a multi-electrode array that's used in the retina. This is a flat piece of glass that has embedded in it electrodes. They're also flat. They don't stick up and poke. But if you have a flat piece of neural tissue that you can squish down onto it, you can record. So these black are the electrodes. The green are backfilled neurons from a salamander retina, filled by Ronen's, I guess. Oh, the retina. Does everybody know where your retina is?
No, I can tell you they don't. I didn't know for 20 years.
Oh my goodness. Nobody in your family had glaucoma. Where is your retina? In your eye. Your retina is a piece of your central brain that happens to be sitting in your eyeball. It's wonderful because it's a very complex piece of neural tissue. It's a little bit unlike your cochlea or your peripheral nerves. It's part of your central nervous system sitting in your eye. It's basically a one-way street out of your eye to your brain. So if you take the eye out and put it in a dish, you essentially have the intact circuitry. So if you can keep it alive, you can take it out. I keep making this terrible motion. You can put it in a dish. Then you can record from it pretty faithfully. Oh my gosh, I just realized as I was making that terrible joke that I forgot to tell you the most horrible joke of the day. So we're going to come back to this. Sodium and chlorine are walking down the street. Sodium says to chlorine, "Crap, I lost an electron." Chlorine's like, "You idiot, you can't tell if you lost an electron. They're tiny, and whatever. And you're always saying you're losing electrons and then you find them, I don't believe you." And sodium says, no, I'm positive. Okay, so this is a recording from the retina. We'll talk more about the retina later. The retina is a flat piece of tissue at the back of your eye that you can put in a glass dish and record from. And if you can get photons of light onto the photoreceptor layers, those are the things in your eyeball that change photons into electrical signals, rods and cones, commonly known, you can see what the brain sees. These are the kinds of electrode arrays you typically use in central parts of your cortex, like your visual cortex, or other areas of your visual system. It looks like a bed of nails. It is like a bed of nails. It's a tiny, tiny thing that you press onto the surface of the cortex. And really, you just press it in. And then you
stuff it in somebody's brain.
You stuff it in somebody's brain and you leave it in there and you close up the hole. And you record. So we've gotten good at this as experimentalists. So we can record from hundreds, if not thousands, of neurons at a time. So we can look at what the brain sees. You know, the history of neuroscience is really combined with the history of modern warfare, because we had to learn about what various parts of your brain do from, well, we originally learned from injury. And to have an injury to your brain that you survive, and I can tell what your deficit is, you have to have a pretty clean cut. So it was explosives that unfortunately let us learn this. So Phineas Gage is the famous for having a traumatic brain injury. He was mining, and you know how you mine, you want to shear off a whole face of rock. So you drill a hole, you put a bunch of explosives along some charges. You've seen this on the sides of roads, right? The cuts. Driving through Pennsylvania or Boulder, you see like parallel lines in the rock. That's where they drilled all the holes to put the explosives. Explode, pulls all the rock away. He was tamping down the explosives, looked away, went off, went through his jaw, up through his frontal cortex. So he had a kind of wonky looking hanging outy eye, and he lost a lot of his frontal cortex. He lived for years. He had seizures, it wasn't great, but the main thing he had were big personality changes. So his frontal lobe seemed to be controlling something about what made Phineas Gage Phineas. Then people realized that if you got a bullet injury here, you would lose vision in this part of the visual field, and so on and so forth. We learned about where memories are stored as we got better at, well, better, as we explored brain surgery to treat seizures. So what people did back in the day, like Hubel and Wiesel here, is they tried to answer the question, what about the stimulus do neurons respond to? So this is a video from the 50s of Hubel and Wiesel showing this light bar to a cat and recording from their visual cortical neurons. So those pops are the spikes played through an audio monitor. Think of Fourier transform. That little blip is going to give you something that pops like that because of like all frequencies. So one of them is holding this bar and moving it around. You can see there's a very localized part of visual space where the neuron responds to, and it's responding to light onsets. And there's somebody coming along, this is a rear projection screen, and I forget if it's Hubel or Wiesel, but one of them is marking, this is how they took data. They're marking the pieces of the receptive field where that neuron responds. You're going to try different size bars. What they noticed there, okay, so apparently there was a little extra. If you have problems with, winging it, should make you feel very upset. So what they noticed here was that in this part of space, neurons were responding to offsets. So if the light is on for a while and then taken away, you get spikes. Whereas this part responds to light onsets. So that's how people looked at what neurons respond to in the brain back in the day. And basically modern neuroscience is trying to get well past this. We've got some fundamental knowledge of what neurons respond to. And now we want to understand how they do complex computation that drives behavior. So a lot of early neuroscience was on the sensory side. How do neurons make nonlinear transforms of their inputs? And is this encoding efficient? And as a physicist, you want to know, is spiking like this the best way to represent blah? And that's what we're going to do in this little mini course. We're going to talk about how a physicist approaches optimality in the brain, and how we start from, what would I do if I were building an engineering system that was going to respond to this stimulus? What if I have biological constraints about the ATP, say, consumption of all those spikes? What if I have constraints about the size of my brain and the wiring that I can put into my brain? What if I have constraints about the fact that I'm an evolved system? So we're going to delve into that. We don't have all the answers because this is modern cutting-edge science. So here's some of the tools we're going to use. We're going to use statistics. We're going to talk about learning and inference. We're going to talk about optimization. We've kind of covered all I'm going to say about dynamical systems, but of course that's a big part of neuroscience. The main stuff we're going to use here is information theory. So I want to give you a brief introduction to info theory. I have some notes on information and spike trains that I'm going to share on the course website that are teched up and a decent read. And some data that I'll have you look at when I pitch you a project tomorrow. Okay, so right now we're just going to do a brief introduction to info theory and then have a little bit of a game. Yeah, I will in just a second. So Ilya said that there's no homework. I actually have decided to give you a few short exercises to see if you're following along beyond the project. It's up to you if you do them or not. But they should be things that don't take you hours and hours. So limited. And if you want to know more, this is a good test. And if you already know this stuff, then you can help your group. So how many of you have ever heard of information theory? Awesome. How many of you feel like you're information theory experts? Okay.
Okay, good.
How
Who was using information?
Yeah, who uses information theory in their research? Oh, goodly number. Okay, so I'm seeing 10-ish. How many of you know about information bottleneck techniques? Looking at you, Carolyn. Okay, good. All right, so since most of you have a flavor of this, we're going to go through it quickly, which is great because we have about 10 minutes left in this part of the course. There are notes that you can read, and we will go through the nitty-gritty in more detail in the next time. So brief introduction to info theory. When is information theory useful? Information theory is just a way of saying I want to characterize the generalized correlation between two variables. And that's all it is. You can think about it as a correlation. So when you want to go beyond linear correlation, you better have enough data to sample. If X and Y are your stimulus and response, you need to have enough data to sample that joint distribution fully because you're not making any compromises about, making a model of that. Information theory can also be useful when you're not sure what your code is. You're not sure if it's single spikes or pairs of spikes or whole temporal sequences of spikes that carry the information either about the input sensory stimulus or the output behavior that you want to know. So here are two variables that are obviously linearly correlated. I would not recommend you use information theory to try to dig into the nuance of this relationship between these variables. Here are two variables that have, I know they have no correlation because I cooked it up that way. So here are two variables that are just random independent variables. They have zero correlation and they have no mutual information. Here are two variables that have zero correlation. Zero correlation, but obvious information, obvious interdependence on each other. Information theory lets you fish out this from beyond that, okay? So that's good. In the brain, this would be sort of perfect synergy. You have to measure both of these to know what they're about, and there's no linear correlation to stand on. In the brain, you sort of have a mix of second order and high order correlations. So entropy is our measure of uncertainty. Entropy is our measure of uncertainty because in Claude Shannon's original work, he laid out some criterion for how he wanted to mathematically define uncertainty, and it turns out that something that went like log p was what you needed to have additivity and branching properties and things like that. And I will share with you again on the course website as soon as I get all the stuff to Dakota some early reading on that. If you look in the appendix of Claude Shannon's original paper, it is very easy to go through his derivation of why entropy is the unique solution to the problems we pose ourselves for developing a mathematical framework for thinking about uncertainty. So here I've put it as the log of n, where n is the number of possible states. So if I'm rolling a die, a regular die, not like a D&D die, like a die from a pair of dice at a casino, how many options are there? 6. So what's the probability that you get a 1 if the die is fair? 1 over 6. So our uncertainty about what will happen goes like log of the number of possibilities. So if we had one of those awesome like 20-sided die, it would be log 20. How high does it go for like role-playing game dice? Go beyond 20? I forget. It's been a while. Ilya? You didn't play Dungeons and Dragons? My view of you is crumbling. But yeah, what is it? What do you? What? How many? When you have like a bunch. Stranger Things is reviving this, right? When you have a bunch of dice that you're rolling in a role-playing game, what's the maximum number of sides you have on a? 20. Okay, so I was fine. I was hoping there were more. All right, fine. 20. It's fake, and they're probably not actually fair. Yeah, they only go up to. You can make 12. You can make 8. You can make. Yeah. I like it. That's good. So we can make a dodecahedron. We can make an icosahedron. We can make a octahedron. And I'm going to stop. Okay. So the log of n, if it's a fair die, then that's just 1 over the probability. That's where we said 1/6. So then that we can just take the minus out in front, minus log p. So now we might not have a fair die. Each, the 5 might be more probable than the 2. So there might be an uncertainty in each outcome. And we just write that as minus log of the probability of that outcome. So if the probability of a 5 is like, I don't know, 1/3, then we want to put that in there. And then to get the average uncertainty, we just average its quantity. So we take the sum of minus log pi over pi. So the average uncertainty looks like this. We're all physicists. This looks a lot like entropy. It's called entropy. That is where the similarities to that thermodynamic quantity really end, unless you're thinking about Landauer's principle for information, the amount of energy it takes to erase bits of information. But for the most part, this is just an analogy because the equation looks the same. We're not using that word entropy in a deep physical sense. Okay? All right. So that is our measure of uncertainty. And we can use that to define our measure of mutual information between two variables. So the mutual information between two variables, A and B, or X and Y, or stimulus and response, or Thierry and Ilya, however you want to define those states that they take on, is just the uncertainty or entropy we have about one minus the remaining entropy we have when we know something about the other. Okay? So it's like the uncertainty we have about rolling the dice minus the uncertainty we have once we know that we're playing with Thierry and he cheats. And the die is really, really heavily loaded. I'm sorry. So if it turned out that he didn't cheat, and the entropy of the die, knowing that we played with him, it was exactly the same, then we have an entropy of A minus entropy of A, and we'd have no information. But if knowing we're playing with him and he loads the die, so that 5 is really, really likely, it reduces our uncertainty about the outcome of the roll of the die. And that's what this equation tells you. Now you can write that out. You can write that out in terms of the entropy of minus p log p and minus p conditional entropy log p. And you can get these kinds of expressions for the mutual information. So you can write it out as a difference of entropies, or you can write it out in terms of this joint probability distribution. Writing out like this shows you the analogy between mutual information, or the relationship between mutual information and the Kullback-Leibler divergence between two distributions. The mutual information is just a special case of the Kullback-Leibler distance, say, between two distributions. I'm comparing their log ratio. And here I'm just comparing the joint distribution to the product of the marginals. I'm comparing the full joint distribution of two variables to the distribution I'd get if they were independent. So I'm comparing the real distribution to the independent model. Okay. Let's see what we're doing next. Okay, so a few more Useful formula, there's a product rule. The joint distribution is a conditional distribution times the marginal. There's a sum rule, which means that if I take and I sum over all the states of B in a joint distribution, I get the probability of A. From there, I can rewrite this. You can use the product rule to write down Bayes' obvious probability identity, or Bayes' rule. It doesn't really need somebody's name attached to it. The probability of A given B is the probability of B given A times P of A over P of B. And that's because P of A comma B is equal to P of B comma A. So I can use that to rewrite this. Here I'm writing out something that's very, very useful. This is a multiply by 1 type arrangement. You guys know when you're manipulating formula to solve things in physics, you do a lot of really standard tricks. You add 0, like if you're completing a square. You multiply by 1 to make a common denominator. And you do some sort of saddle point approximation. That's basically all you need to know. That is physics. So here is just an example of expanding out this PB, so I maybe I want to rewrite that. More useful formula. The entropy of two variables jointly is equal to the sum of their entropies if and only if the joint distribution is the product, if they are independent. There's also a chain rule for entropy that's useful, that's easy to convince yourself of. And here is the the DKL between two distributions P and Q. It's just P log the ratio of P to Q. It's the extra bits you need to represent P in Q, in the Q basis, in the Q support. And here the mutual information is just a special case where P is the joint distribution and Q is the independent model, the product of the marginals. Because of the Jensen's inequality, mutual information must be positive. You can never have more entropy by measuring something than you had before, which is perhaps obvious. I'm done. I'm going to give you an exercise. I have 3 minutes, Alex.
No, Ilya said you started early.
Why would you do that? Do you want the game or not? All right, fine. So next time we're going to be talking about some info theory basics, and we're going to talk about Maxent distributions. But to get you thinking about that, I want to give you a puzzle weighing problem. All right, so here is your puzzle. You have 12 coins. You have probably seen this before, but I want you to try to solve it in a new way. Okay, you have 12 coins. One coin is counterfeit. Counterfeit, meaning it's not gold coin, it's made of some other metal, usually just a little bit heavy or a little bit light. Okay, you are given a balance. Simple balance, where you can put some number of coins on the right or left side of the balance and you see if it tips up or down. It does not tell you a weight. It's just a simple balance. So you need to tell me which coin is counterfeit. Counterfeit. Which coin is counterfeit, and is it heavy or light? And you need to do this for the general case where, don't tell me about the lucky case where you happen to pick the one that's counterfeit and put it on a balance of one that's not and get all the information in two weighings. You need to tell me, for the general case, what's the minimal number of weighings you can use to answer both those questions, independent of how I shuffle the coins for you at the beginning. And what would Shannon do? What would Shannon do? You want to maximize the amount of information you gain on each weighing. And how are you going to do that? So what would Shannon do? he would max info in each weighing. So think about the things you can and can't control here, and let's talk about that on Wednesday when I am back with you for the second part of this mini course. And I've decided I'm on time, so thanks. Yay.